All right, we're going to continue on our unit with radicals and rational exponents, and guess what we're going to get into? Rational exponents. Yay. There's a lot of background stuff to cover before jumping into these two examples, and the first thing I want to show you is a little fact that you may or may not know. And the fact is, and this is going to be weird to see, but the fact is that any operation that you perform with numbers can be expressed with its inverse operation. And that's kind of weird to hear or see. And once I show you a couple of examples of this, it's going to make a whole lot more sense. But as long as you can see that note and wrestle with it, it's going to make a whole lot of sense. So let me give you a couple of examples on this note. This is a fact. Okay, so for example, if I show you an operation like subtraction, right? You can't deny that that is subtraction. Can I express that subtraction as its inverse? Can I express that subtraction as addition? And of course I can, right? If I have 7 minus 3 using subtraction, I can express that as addition. I can express that as 7 plus negative 3. Same thing, right? It's going to be the same thing. I'm expressing that subtraction as addition. And the same thing can be said for subtraction. If I had, addition. If I had 8 plus 5, no doubt that is addition. But can I express that particular use of the operation with its inverse, with the inverse of addition, which is subtraction? And of course I can. I can call that 8 minus negative 5, and I'm able to express that addition as subtraction. That's just a fact of inverses. Okay, and so the same thing holds true for multiplication and division. I'm only going to show one example of that, just to drive the point home. If I had this operation, this of course is division, but can I express that division as multiplication? This is 5 divided by 7. Can I express that using multiplication? And of course I can. That's 5 times 1 over 7. And so I have that particular operation of division being expressed as multiplication. So again, any operation can be expressed with its inverse. So what about more operations? Are there more operations? Absolutely. Absolutely there are. For example, when we were doing previous work on solving equations, we would come up with a situation like this. You know, if we had x squared equals 10, how did we solve for x? You know, how was it that we would get x by itself? We would undo the second power. And the way we would undo the second power is by taking the square root. And if we take the square root of one side, we take the square root of the other side, and then we would have x equals, you know, whatever. It doesn't matter. Yeah, you can put square root of 10, but that's not the point. The point is to undo second power, we took the square root to get x by itself. Now we can start to think about, well, let's use some current material now. What if we had something like this? X to the 5th power is equal to 12 or whatever. It doesn't matter. Okay, so if we had x to the 5th power equals 12, how in the world can we undo the 5th power? And you start thinking about current material from the previous notes in this unit, and hopefully you can come to the realization, hey, if I take the 5th root, of x to the 5th power, wouldn't that give me x? Absolutely. And so to solve for x, I would take the 5th power, or the 5th root, on both sides. Okay, so that's how we would solve for x in that case, and then we'd have x equals. And again, it doesn't matter if the 5th root of 12 is. What the point is that we have more operations and their inverses. And so we have an operation with an inverse, and let's say if the operation was a power, what is the inverse operation of a power? And that, of course, is a root. Okay, and if it's to the second power, it's the square root. And if it's to the third power, it's the cube root. And if it's to the 5th power, it's the 5th root, and so on and so forth. And it's the same thing going from roots to powers, right? How can we undo the square root? Second power. How can we inverse, the 10th root? 10th power. And so we have more operations and their inverses, and there's many more than this, but that's again, just to emphasize the point that any operation can be expressed with its inverse. Now, how would that work with using powers and roots? Well, let's take a look at this. How can I express 3 to the second power using a root? Right? So how can we express that? Well, that's the same thing as, right? This is the same thing as the square root of 3 to the second power squared. What? Well, yeah, that's what it is. It's the same thing, right? This is 9, this is 9, doesn't matter. Okay, so we have 3 to the second power is the same thing as the square root of 81. So there we have. It's the same exact thing. So that's going to lead us to a note on rational exponents. Okay, so understanding that any operation can be expressed with its inverse, we can now get finally to a note, right? Finally, cats, good Lord, will you just be quiet and get to note taking? If we had any number being raised to a rational exponent now, okay, so now we have the whole existence of a rational exponent. Any exponent that we've ever dealt with is rational, by the way. If we have any number being raised to a rational exponent, and here's the note for rational exponents, how can we relate that to radicals? Okay, so what's happening with this rational exponent? We have the numerator of the exponent, which does represent the power. But what's the deal with the denominator of that exponent? So the denominator of that exponent is actually the index of the radical. So if we have any number being raised to a rational exponent, we would have the numerator of the exponent being the power, the denominator of the exponent being the index, and then we can express this in 2 different ways using radicals. Okay, so we could have the radical of a, where n is the power, and n could be under the radical, and m as the index, and of course the index is there. So we could express it that way, or we could also express it this way. We can have the radical with a. Of course, m is still the index, but this time we can express the power on the outside of the parentheses using the law of exponents. All right, so that's just the equivalency of it. And if you don't believe me, let's go back to this. Okay, so how in the world is this going to work? Okay, so remember how this was the same, right? So what is the square root of 3 to the second power to the second power? Well, let's use laws of exponents, right? 3 to the second power to the second power is 3 to the fourth power. And what's the index here, right? Square root, the automatic index is 2. So wouldn't this be 3 to the fourth power with an index of 2? And why, yes, it is. And guess what 4 divided by 2 is? It's 2. And holy cow, Mr. Katz, you just blew my mind, right? So that's how the rational exponents work. Okay, so just one quick example, and then we can jump right into the problem. So here's a quick example. If I gave a number like this, 9 to the 1/2 power. Okay, so what we can do is look at this in 2 different ways. We can look at this in the first way, where we have the square root of 9 to the first power. That's looking at it this way. Or we can look at it this way, where we have the square root of 9 to the first power. Okay, so we can look at things that way. And it doesn't matter which way, because in one way we're taking 9 to the first power, which is 9, square root of 9, which is, of course, 3. Or we can look at it the second way, the square root of 9, which, of course, is 3, raised to the first power. Doesn't matter. We're still going to get 3. So just like everything else in this unit, there are multiple approaches to each of these problems that we can use. Again, finally, cats, be quiet so we can do some work. Okay? Yes. Let's do number 1. All right. So now we have this first question, number 1, and this crazy number with a with a crazy exponent, and how are we going to figure out what that is? Now, based off of the note that we just took, there are a couple of things that we can do. Based on the note that we just took, there are a couple of things that we can do. We can use what we said. We could say, well, we then would have the fifth root of 32 raised to the negative 3 power. We could do, the fifth root of 32 raised to the negative 3 power. You can do either of those approaches. I'm not going to. I'm going to use one of the laws of exponents. Do you remember the law where if we had a negative exponent, all we do is switch from numerator to denominator and vice versa? So I'm going to exercise that first. I'm going to use my law of negative exponents right away. I'm going to go ahead and call this 1 over 32 to the 3/5 power. Now, do you have to? No, you don't have to. Okay, you can use either thing. Okay, but eventually you're going to have to use this law at some point. And just like for me, do I have to use the radical right away? No, eventually I'm going to have to. Okay, so it doesn't matter which way. So for me, when I do that first, I'm going to eventually have to use the new note, where I have the fifth root of 32, and then I'm going to raise that to the 3rd power. And that's the way I'm going to approach it. So even if you chose to do this first, I'm down with that. All right, do I have to? No, you don't have to, but I'm totally down with that. Because now what we have to do is remember the fifth root asks a question. The question is, what number times itself 5 times gives us 32? And the number that when you multiply it by itself 5 times gives us 32, that particular number is the number 2. And so we have 1 over 2 to the 3rd power. Okay, so when we have 1 over 2 to the 3rd power, you know what 2 to the 3rd power is 1 over 8. Okay, so this whole thing is going to shake out to be 1 over 8. And that's how that works. It looks crazy. There's multiple ways to do it, and it doesn't matter which way you use. So many ways to get to the same answer. All right. So now we're going to approach number 2. Sorry for that pause. I'm working with students. All right, so here, let's take a look at number 2. How in the world are we going to use that? So we have the second problem, not really a problem, but the second expression that must be simplified is going to get a little nuts. It's going to get a little nuts. So, and just like before, many different ways to approach this. No matter what, we're going to have to use the note that we took, and we're going to have to use a couple of laws of exponents. So you can right away, if you want, go ahead and exercise the note we just took. If you want to take the second power, okay, you want to take the square root, second index, right? So the square root, second index, square root, to the 3rd power, you can do that. You can do that with everything. Okay, so you can call this the square root of, 9x times the 4th root of y, all to the 3rd power. You can do that, right? You might be hesitant about, well, what's the deal with the radical inside a radical? And we'll get to that in a second. Okay, you can do the same thing, call it the second root of 9x times the 4th root of y, all of that raised to the 3rd power. You can do that as well, but I'm not going to. Okay, I'm not going to do that because I'm going to go ahead and do something that we're going to have to do eventually at some point anyway, and that's address this little thing. What's going on with the radical with a radical? I'm going to go ahead and use the note we just took first. Now remember this note. We can operate this note going in this direction. We can express a rational exponent as a radical, and we can also use the note going the other way. We can take a radical and express it as a rational exponent. And I'm going to do that first. That's the first thing I'm going to do. So I'm going to leave my 9, my x, the same, but I'm going to take care of this 4th root of y. I'm going to make that a rational exponent. That means I'm taking y, and I'm taking the 4th root of y, okay? But what would the power be, right? So what would I have in the numerator of that rational exponent? It's only y to the first power, so y to the 1/4. And that's the first thing I'm going to do. And when I do that first, that's going to help out a few things. Now, some people may be thinking, well, the first thing you would have done is what I'm about to do. And that's using another law of exponents. And if you remember this law of exponents, where you have a times b to the nth power, it's the same thing as a to the nth times b to the nth. We can use that law. I'm going to use that law now. Okay, so now I'm going to have 9 to the 3/2 power times x to the 3/2 power times y to the 1/4 to the 2/3 power. Okay, so I'm going to go ahead and use that law, which brings up another law of exponents. The other law of exponents is saying that if you have a to the n to the nth, raising a power to a power, that's the same thing as keeping the base and multiplying the exponents. I'm about to use that right here. Okay, so I'll get to that in a second. First, let's take care of this. What in the world is this? This can be looked at, again, at two different ways. You can call this the square root of 9 to the 3rd power. Knock yourself out. I ain't doing that, because I'm going to look at it this way. The square root of 9 to the 3rd power. Isn't that a much easier way to look at that? And yeah, square root of 9 is 3. 3 to the 3rd power, of course, is 27. All right, so we have 27. And then we have x to the 3/2 power. We can leave that for now. And then what are we going to do with this? Okay, so y to the 1/4 times 2/3. I'm going to exercise this law of exponents. And I have y to the 2/8. Or I put this upside down. Holy cow, I made a boo-boo. So finally, you guys that have been clamoring probably all video, cats, that's upside down. It would be, finally, I can fix it. So y to the 3/8. There you go. Does that make you feel better? I know many people are watching this video just yelling either at your screen or at me, but there, I fixed it. So we have that, and that's fine. If we were looking for the answer in rational exponents, we're good. Okay. If I said express the answer in rational exponents is good. But just out of curiosity, what if I said express your answer in radical form? How in the world would that look? Okay, 27, of course, stays 27. But then how would we do in radical form x to the 3/2 power? We'd have the square root of x cubed. And how would we do the radical form y to the 3/8 power? That would be the 8th root of y cubed. Now this is where things get weird. Can we combine these two? No. Apples and oranges. Index of 2, index of 3. We can't. Apples and oranges. But what we can do is do something with the square root of x to the 3rd power, which is the square root of x squared times the square root of x. And we could do something with that. All right, so we'd have 27. The square root of x power, or the square root of x squared is x, and then we'd have the square root of x. Trick, be careful. Even index, odd exponent, we need absolute value bars. And then we'd have, well, the 8th root of y to the 3rd power. That's all we can do in radical form. It looks really bizarre, but seriously, there's nothing else we can do. Okay, so if I said, express it in rational exponents, bam. In radical form, bam. And that's it for rational exponents. So if you do your homework, it's just like with everything else. I mean, do your homework at the practice. It's going to get a whole lot more manageable. Thank you.